Can I invite the next speaker, Kevin Peddie, who is talking about wind, use of, no, not wind. He's working in a wind center, but he's talking about natural ventilation.
Good afternoon, everyone. Today I'll be talking about natural ventilation for, well, I guess not super tall buildings, but more tall buildings in regards. Natural ventilation design is something that is able to help the efficiency of the building after construction. Now, a lot of these things aren't generally taken into account during the actual design process at an early stage. With a lot of times that we've been approached by architects or developers, we've been asked to come in after the development's already put in concrete. Now, this does have a substantial effect on the design and the actual performance outcome. Natural ventilation is something that's very much reliant on the location of the development. The building's location with its surrounding terrain, surrounding buildings, its local climate as well, is very dependent on what sort of output will be generated due to the flow through a residential apartment. Now, ANSI and ASHRAE 55 provided guidance for what thermal conditions will be suitable, because there's two main key areas for natural ventilation, and this is both the air quality and also the thermal comfort of an occupant. So when you think about it for yourself, you're in an apartment, either in a hotel room or so forth, the main thing you're looking at is the room too stuffy to breathe adequately, or is it too hot, too cold? They're the two main areas that you'll have concern. These applies both in your own home, apartments, hotel rooms, and the like. Now, there's certain levels of allowances in these different temperatures or suitabilities that you'll be willing to handle depending on what control you have over the situation. If you're in an environment where you can't control, say for instance in this room at the moment, you can't control the temperature, you'll feel slight changes in temperatures while you're in this room. However, if you're at your own house and you feel slightly too hot, you're more welcome to get up, walk to the window, open the window. And you feel the temperature might be not that much different, but you feel in control of the situation. So you're willing to have different, slight different variances in your body temperature. The other thing to think about as well is whereabouts in the world is it? You could go to, for instance, in Australia, there'll be certain temperature ranges that'll be occurring, not just times of the year, but also times of the day. I guess we have quite a mild climate in Australia whereby the temperature at night, temperature during the day doesn't fluctuate substantially. But then if you look at, say, for instance, the Middle East, during the hot summertime, during the day it's extremely hot temperatures, whereas during the night, due to the clear air, the temperature dissipates quite quickly and you get quite cold nights. So there's different processes that can be done which can be looked at the actual location of the development. But in the end, the actual local climate is the key driving factor as to how this can be done. However, it should be noted that it's not always the local climate, natural ventilation can't always be the end factor. It's a lot of times is married in with a HVAC system and helps reduce the cost of it. I'll now just show you, for instance, this is Sydney. I'll look at this is in the morning and then I'll show you an example of in the afternoon. The way that the ANSI sort of look at it for temperature differences is it looks at the mean minimum temperature and the mean maximum temperature and takes a look at a survey that was done to look at 80% acceptability by different occupants and also 90% acceptability by occupants. So there's not really a strict guideline or criteria, it's more just getting the majority of people satisfied with the local conditions. Now you can see for Sydney here, during the summer months of the year, the mean daily temperature here and the mean daily minimum temperature as compared to what the acceptability ranges are, they can be satisfied. However, when you start looking at the winter months, which for Australia is June, July, we now start to actually fall outside of these ranges. So people actually start to find it actually becomes too cool for their liking. I'll show you now an example of this is in the morning, I'll show you an example in the evening. Now you can see here it now extends a little bit further, not just for June but also July and August, that this sort of extends where you have this issue. However, I actually had a personal experience of this, buying a new house start of the year, or not a new house, a house that was technically termed has potential. The previous occupants had a total of 14 vents located on different aspects. This is beautiful during February when I bought the place. The house was nicely aerated during the day when I was out. Came home at night, I felt fine. However, coming into June, July, I started to notice airflow was not really what I wanted during these times of the year, so that was quickly found with a bit of gyprock to hide all those holes. So as you can see, the difference, or the aspect I had to take was, I found it too cool, I have to close this system down. However, the benefits I was finding at different times far outweighed these other circumstances. However, this could be controlled a lot simpler than closing off a fixed vent. It can be used through an operable window. Other benefits of natural ventilation is not only just for the occupants themselves, but also running costs. One of the examples that was actually, a study was done whereby they looked at the effects of taking a new development and designing it to be naturally ventilated as opposed to a retrofitted development. Now, for a new development to take into all the procedures, a cost per occupant is about $1,000 per person to do different changes. This might be due to additional window openings and so forth that need to be put in, so additional costs associated with that. However, to retrofit a new development, you're looking at about $3,500 to $4,000 per occupant. However, when we look at the benefits that come with this, the study is actually done where the benefit for health showed about $60 per occupant, not much to say. For energy, it's about $110 per occupant per year. So it's still not weighing up too well. However, the further study they actually found was that the productivity in an area where not just a person because they actually live there and also an office-based setup, the productivity showed they actually had a benefit of about $3,900 per person per year benefit. The way this is measured is by looking at a couple of different factors. It's the actual absentees from work. I found that for a building that's designed for natural ventilation has 70% less absentees who go to work. This is due to better air quality. Because when you look at it for a mechanical system, if you have a mechanically designed room, the air changes through a space has to be in the range of about 5 air changes per hour. This is purely because the quality of the air that's being pumped into the room isn't as high nature, and such that you're getting fresh outdoor air for a naturally ventilated coming in through the room and exiting another avenue. The other benefit that was seen is, that leads from this, is what's known as sick building syndrome, and that saw a reduction of about 40 to 60%. What sick building syndrome essentially is when you have the quality of the air makes a person slightly lethargic, more prone to illness and so forth. So by just developing your building to be smarter, it's not just the energy performance that's been benefited, but also the actual occupants of the building. The other thing to note that's very interesting is the global trends in the existing buildings to meet specific standards of energy, and this obviously varies from different parts of the world. The benefits that come up is not just the end game, so the occupancy levels, because the more green efficient the building design is, the lower the vacancy rates are for those buildings. However, it's also the rental price for energy efficient design is a lot higher. The selling cost is a lot higher for those. A perfect example of this is in Australia's capital down in Canberra. There's a vacancy rate of 11% for a commercial building. You think, gee, that's relatively high considering this is where our parliament is, so it's heavily dominated by government employees. However, when he actually looked into that a bit further, of that 11%, there's 2% component is for buildings that are designed for a high level of energy efficiency, while the remaining percentage is the buildings that are pre-existing older buildings that haven't been retrofitted. So you start to see, just by designing more energy efficient building, the owners and so forth are getting a much greater return, not just by high levels of occupancy, but higher rental returns as well. Now, natural ventilation criteria really depends on what the building is and what the intended use of a space is. So it could depend on the size. So the requirements for this room here, which is to be utilised by a larger number of people, as opposed to, say, a bedroom or a study or something like that, is obviously going to be different. The intended number of occupants of the room, the materials that we used within that room, because materials themselves give off an odour. So that odour there needs to be actually transported outside, otherwise it creates that stuffy smells inside. Now, this generally equates to about 1 to 2 air changes per hour for air quality. And this is going based both off the ASHRAE standard, also off the Australian standard. Now, there's a separate criteria which is for thermal comfort, which I mentioned previously, which is ASHRAE 55. Further to these criteria, there are also sometimes for some areas local planning requirements. Some of these might be that for a development itself to be considered naturally ventilated, you may require up to 70% of units satisfying these naturally ventilated needs. However, a lot of the time, the actual planning requirements don't actually know the nitty-gritty of how efficient a building should be. For instance, local planning in Sydney itself, which I'll be showing some case studies for coming up, actually says for a building to be naturally ventilated, you need to achieve 60% of apartments need to be considered naturally ventilated. Now, for an apartment off plan to be considered naturally ventilated, it needs to be a corner located unit, so openings either orthogonal or opposite aspects, or it needs to be a double-storey unit with a second-storey step back. Now, trying to achieve that on a high-rise building where you might have large number of units which are on single aspects. Now, to virtually achieve that, you've got to have very small floor plates, or you have to do extreme changes to your whole design. The other option they actually put in there is if your design falls outside this, you need to prove that you still think it'll work. That's where the benefit of wind tunnel testing does come in, which we've been brought about on numerous occasions. Now, modelling techniques that are done is to look at, the pressures between two different openings, as well as the velocity, the wind velocity for that local area. Now, this is just so you get an idea of what sort of are the driving factors for a location. These bottom areas here, the CD is what's known as the discharge coefficient, so the efficiency of airflow to go through an opening. This varies depending on the opening size, the shape, and any other objects that might be covering that opening, whether it's a fly screen and things like that. And the second component is the area of that opening. Now, I'll go through a couple of different case studies whereby natural ventilation is being considered at different aspects of the design. This first development is, it's only, as I was mentioning, it's only relatively small in the grand scheme of things, it's only being 25 stories in height. It's located in Parramatta, so that's essentially what's known as the second commercial hub of Sydney. It has numerous single aspect units on the eastern and western aspect. Now, to get an idea of what the driving factors for Sydney are is during the warmer months of the year, as I was showing previously, where you'd want to use natural ventilation, the main winds come from the northeast and southerly directions, with the westerly winds becoming more prominent during the winter months. Now, for testing of this development, prior to doing testing, we actually met with the clients very early on. There was an initial design scheme done for this development, and then new architects came on board and they went, right, this is what we want to achieve, this is what the client wants in the end. What do we need to do to achieve these aspects? So the first thing we sort of looked at was, I'm just showing this, go. On these areas here that have large setback in sections. So we looked at using that to be able to generate pressure differentials. We recommended having large step facades to make use of the northeasterly winds generating pressure differential between openings. This has been done on numerous occasions. So the requirements for this area being located in Sydney, so based off for thermal comfort, change in temperature about 2 degrees, so equates to about a 0.4 metre per second flow through an apartment, and also 200 changes per hour. Now, we provide initial design recommendations, however this was altered due to internal layout of the building that needed to be changed, so it ended up only being 2 of these setback sections were able to be used, so it's only 52% of the apartments were able to achieve natural ventilation. Whereas previously we also tested the original design and they were able to achieve up to about 80%. So you can see just facade changes can have severe effects on these. However, additional recommendations were done and tested whereby we look at a ventilation shaft, essentially located at the rear of the apartment, and it works off pressure differential between the facade of the building and also a negative pressure region at the roof of the tower. I'll go through this in a bit more example in my third case as to how this works and the studies we did. This essentially is just a diagram of showing how the flow path ended up working. So you have a high pressure region at the main aspect of the tower, in through the window areas and out up through the back. So you get flow through the whole apartment. These ventilation shafts are broken up to the 3 levels, essentially because as you go up the building, you get different pressure regions going up the tower. So if you just use one single shaft, you can have essentially a short circuit at the top of the tower. This is another development. It's a 42-storey building located in Chatswood. Couple of interesting requirements for this job was it's located hard up against a railway line. So they had strict requirements as to window opening sizes that face that, due to the rail authorities' safety concerns of people actually jumping onto the railway tracks or throwing things onto the railway tracks. We've actually provided initial input into this as to provide solar access requirements for the apartments as well, which provided some slight facade articulations. So we ended up providing recommendations as to window opening locations. Some of the window opening locations end up putting windows for the same apartment in the same pressure region. So just by simply changing where openings are located can help provide a pressure differential between those apartments, even for single aspect apartments. Also pushing facade lines out to the very edge of the glass of the building profile and having a second, virtually a setback balcony area to generate your own pressure differential. This last case study I'll go through, it's actually quite a shorter building. The other two are still currently going through construction. This last one's, it's only 17 stories in height. Essentially, it's 2 buildings connected by a central link bridge. Now, this building here, I'll be talking through a case study for a unit apartment located just here. Now, the unit itself has numerous windows for the individual units. However, they all face the recessed balcony area. And the external balcony has a top hung window, so very inefficient for airflow to go through, whereas the other areas had large sliding doors, so very free flow. However, the apartments weren't satisfying. For this development, we recommended that we look at either putting a rear-mounted ventilation shaft or changing window configurations. The client themselves ended up going with the ventilation shaft. They were themselves a bit sceptical for it, but we proved through wind tunnel testing that it can work. Now, there was also one of the other concerns was they came at a later stage, put all sunshade features on the balconies, which can be operated by the occupants. Now, when we did the testing, we were able to prove that it was able to satisfy ventilation for these occupants, and they were able to control it. However, it always comes down to, does it actually work? So, as I was mentioned before, the apartment I'll be talking about is 601, which is located just here. So it's a 2-bedroom apartment. I'll just show you a bit closer. This is just the southern aspect of the tower, so the other tower is located up towards my end. This is a closer view of the tower. So there was sliding doors located for the 3 aspects, so main bedroom, second bedroom, and the living space, all linked towards a recessed balcony area, while there was a top-hung window which was located further out. We had recommended at the time a relocated ventilation shaft, which they actually were able to install at the back area located in the master bedroom. Now, this is able to be put in the master bedroom purely because this is a single unit. Obviously, if this had multiple people living in these areas, you might have to look at a different location. Now, we did full-scale testing for this development after it was actually completed, whereby to measure the actual flow through from the window opening through to the ventilation shaft to make sure, firstly, is the flow working properly? Because concerns with the rear-mounted ventilation shaft is, and which is shared to other levels, is there'll be smell issues, there'll be fire issues, there'll be noise issues. However, we went through this with acoustic engineers to be able to line the actual ventilation shaft to minimise noise issues. Special one-way, single-way louvers were designed to be able to have it so the flow just goes from the apartment to the ventilation shaft. So we have to make sure that the flow itself is actually working that way, otherwise there'll be no flow. And finally, the fire component. So fire dampers were able to be put inside the actual shafts which were taking into account the fog assault. So the effects of that on the flow itself were also addressed. We undertook smoke trace studies for this building for over a large period of time to look at varying effects for different wind directions. Now, you can see from the very bottom here, comparison between wind tunnel study and also the full-scale testing. And they actually are very close. You can see here, full-scale testing shows a flow through the apartment of about 0.7 to 0.9 metres per second. And bear in mind that about a 0.4 metre per second flow is all that's needed to be achieved. While wind tunnel measurement showed a 0.7 to 1 metres per second. The second bedroom, which is located closer to the lounge room, showed a flow of between 1 and 1.2, whereas the wind tunnel measurement showed something was slightly less than this. However, and this is quite the opposite for the living room. However, overall, the results are quite close. And you start to think, well, okay, why is this the case? Why is the flow slightly different, like those slight changes in the two aspects? Now, one of these cases is the internal components that the actual occupant had within the unit, within the living space, changed the flow component. So the way we had the internal design that the architects had originally planned had changed. So the actual internal flow needed to be reassessed. When we reassessed it, took this into account, these matched up again. One of the other parts that was done was this is based off wind speed data that was obtained from the local airports. Now, these are only provided in half-hourly intervals. They're not a full record trace, and they're also just a local weather station. So to provide a more accurate reading for the actual weather station for the exact precise time the testing was done, this would perhaps also reason as to why the results are slightly different. We might have been testing at the time for the living room during an event where it was slightly calmer conditions as opposed to what was being measured during that interval. But in the end, this is able to show that you can actually design a high-rise building with numerous single aspects and still be able to satisfy occupant comfort for both thermal and air quality. Thank you.
Thank you very much, Kevin.